All right, guys, we're back with another Algebra 2B lesson. Today we're talking 11.2, Theoretical and Experimental Probability. This is a really fun thing for me. This is one of the fun things about 2B is probability. I think it's just cool. You actually learn something that, who knows, you might be able to use. Anyway, let's talk about what probability is. We're going to look at theoretical probability and experimental probability. And when you're back in the classroom after this remote break, we are going to do some probability experiments too. It's going to be fun. All right. Anyway, probability is the measure of how likely an event is to occur. Each possible result of a probability experiment is called an outcome. The sample space is a set of all the possible outcomes, and an event is an outcome or a set of outcomes. So how does this work? All right, so there's various probability experiments that you can perform. You can roll a number cube. You may know it as a die. There are 6 possible outcomes. So the sample space is the numbers 1 through 6. And every time you roll that die, that is an event. And what you roll is an outcome of that event. This here spinner has 4 colors. Sometimes you've probably seen spinners. Oh, the game of life, right? You spin the spinner in the game of life. There's 4 outcomes here: red, blue, green, yellow. That is your sample space. When you spin, it looks like they spun red, so their event is red, and that is the outcome. Probabilities are written usually as fractions or as decimals between 0 and 1, or sometimes they're written as percents. Now here's the thing. It's always going to be between 0 and 100. You can't have over 100% for a probability. It's not possible. You can't have less than 0. It's not possible. An event will be totally impossible that has an outcome of 0, 0%. The fraction is 0. If it's just as likely as it's not likely, it's 50%. So we're talking 0.5 or 1/2. We're halfway there. And it is absolutely certain to happen. The probability will be 1 or 100%. Equally likely outcomes have the same chance of occurring. So when you toss a die or a coin, you toss a coin, you get heads or tails. They're equally likely, as long as the coin is fair, because sometimes coins aren't. Favorable outcomes are the outcomes in a specified event. For equally likely outcomes, we have what we call theoretical probability of an event. It's the ratio of what you want, favorable outcomes, compared to the total number of outcomes. So, what you want divided by everything that could happen. So like this one here, a CD, oh, I love this one. A CD has 5 upbeat dance songs and 7 slow ballads. What's the probability that a randomly selected song is upbeat? All right, so what are the total number of songs? 5 plus 7 is 12. So there's 12 possible outcomes. If you hit shuffle, what are the chances of you getting a nice upbeat dance song? 5 out of 12, or about 41.7%. Here we have a sample space where we were rolling 2 number cubes, 2 dice. A red number cube and a blue number cube are rolled. If all the numbers are equally likely, what's the probability the sum will be 10? All right, so rolling the dice, notice there are a total of 36 possible outcomes, everything from 1-1 to 6-6. How many different outcomes give us a sum of 10? 4 and 6, 5 and 5, 6 and 4. There's 3. So 3 out of 36 would give us a sum of 10. So we have a 1 in 12, 1 out of 12 chance of rolling a sum of 10. If we look at the note sheet, here it is. You can predict the likelihood of an event will take place by calculating probability. In order to calculate probability, you need to know all the possible outcomes of the event. So it's n over t. It's the number of favorable outcomes divided by the total number. If you toss a dime, there's 2 possibilities, heads or tails. If you roll a number cube, there's 6 possibilities. If you draw a card from a full fair deck of cards, there's 52 outcomes. Jokers don't count. Randomly choosing a day of the week, 7 outcomes. So let's take a look at this. Identify the N and the T in each statement. There's three black kittens in a litter of 6. So N is 3, T is 6. 8 donuts, 2 are chocolate. N is 2, T is 8. Half the children in a 16-student class are girls. All right, so N is going to be 8. T is 16. How did you do that? What's half of 16? It's 8. Harry put a silver dollar in 4 out of his 12 grab bags. So, I want a nice shiny silver dollar. There's 4 out of a possible 12. We'll get to complement in a minute, but let's take a look at probability in more detail here. Probability measures the likelihood of an event or the outcome. We already talked about this quite a bit, but here's another possible sample space. Let's see, what if you want a sum to be 8? All right, so there are actually, let's see, 1, 2, 3, 4, 5 different combos that add up to 8. So our probability of getting a sum of 8, it's going to be out of 36 again. 8 out of 36. All right, did I say 8? 5. Where am I getting? All right, let's take a step back. The sum is 8. There are 5 combos that give us 8, so it's 5 out of 36. Let's see. 2 number cubes are rolled. If all numbers are equally likely, what's the probability the sum is 3? All right, so let's go back up here and let's look for a sum of 3. Where are we going to get 3 from? Let's see, right? Whoa. Here. 2 plus 1 or 1 plus 2. That's the only way we get 3. So how many are there? There's 2 ways. So that's going to be 2 out of 36 or 1 out of 18. All right, let's see. The sum is 4. Let's go back up. Let's see, how do we get 4? Well, 3 plus 1, 2 plus 2, 1 plus 3. Those are the combinations that would give us 4. How many are there? There are 3. So it's 3 out of 36 or 1 out of 12. If the sum is 9, 9, what is it? God, 9. That would be right here, 6 and 3, 5 and 4, 4 and 5, or 6 and 3 and 6. 1, 2, 3, 4 possible outcomes out of 36. So 4 out of 36. That is 1 out of 9. Right? 4 divided by 36 is, yeah. All right. So complementary events. Let's go back here. An event of all possibilities in the sample space is always going to be 1. The complement of an event, E, is the set of all outcomes that are not E. So sometimes it's easier to find the complement than to find the probability of an event happening. So the probability of the complement is going to be 1 minus the probability of E. So if you've played the game of Battleship before, you are aware that you've got 5 ships on a 100-hole grid, and players are going to try to guess the location of their opponent's ships and then sink them. At the start of the game, what's the probability the first shot misses all the targets? All right, let's take a look at the table here. Destroyer's got 2 holes, cruiser has 3, submarine has 3, battleship has 4, carrier has 5. So it's a total of 17 holes. So they have a 17 out of 100 chance of making a hit. What's the probability that they miss? It's going to be hard to figure that one out unless you know, well, subtract from 1. 1 minus 17 out of 100 is 83 out of 100. So the probability is 83%. So if we look back at the note sheet here, the complement, what is the complement to rolling a 3 on a number cube? How many ways can I roll 3 on a single die? 1. So the complement would be 1 minus the probability of rolling 3. That'd be 1 minus 1 out of 6, which would be 5 out of 6. Fred has a bag containing 12 black, 10 red, and 15 white marbles. He wants to know the probability of randomly selecting a red from the bag. What are the unfavorable outcomes? They are, well, black or white. So if we figure that out, let's see, there's a total of, that's 12 plus 15, 27 out of 37. So let's see, write the formula to find the complement of choosing a red. Let's see if that works the same way. 1 minus 10 out of 37. Yeah, 27 out of 37. Same thing. I don't know if it's necessarily easier to find the complement here, but trust me, there are definitely ways where finding the complement is definitely easier. All right. So you could also use permutations and combinations to find probabilities, and that's why we learned about them in lesson 1. Let's take a look at this. Each student receives a 4-digit code to use library computers. No digits repeated. Manu received the code 7654. What's the probability he would receive a code of consecutive numbers? All right, so determine whether the code is a permutation or a combination. Order obviously is important because we're talking about consecutive numbers, so it's going to be a permutation. So find the number of outcomes in the sample space. The sample space is the number of permutations of 4 out of 10. So 10 pick 4, that'd be 5,040. What are all the favorable outcomes then? 0, 1, 2, 3, 1, 2, 3, 4, 2, 3, 4, 5, 3, 4, 5, 6, 4, 5, 6, 7, 5, 6, 7, 8, so on. There are 14 possible favorable outcomes. Why 14? Because consecutive, they didn't say whether we're counting up or we're counting down. So there's 7 ways to count up, and then count down, there'd be another 7, so there's a 14 possible ways. So what it would be the probability that he would get consecutive numbers? So it would be 14 out of all the combinations, 5,000, I should say all the permutations, 5,040, 1 out of 360. So there's 1 in 360 chance that he would get consecutive numbers. A DJ randomly selects 2 of 8 ads to play before her show. 2 ads are by a local retailer. What's the probability she will play both of the retailer's ads before the show? All right, so this would be a combination because it doesn't order doesn't matter. So you would have 8 choose 2, and that would be, let's see, 8 choose 2 is, I'm sorry, 8 divided by, there's 28 different combinations of ads, and in order for them to both be from the same, there's only one way they can be from the same retailer, so it'd be 1 out of 28. There's geometric probability, which isn't in your note sheet either. This is a form of probability that's a ratio using lengths, areas, and volumes, like this rather bizarre looking figure here. All right, 3 semicircles with diameters of 2, 4, and 6 centimeters are arranged as shown. What is the probability at random that a point is inside this shaded region? All right, so we have to figure out what the areas are. And in order to figure out geometric probability, it's usually the area of what we want divided by the total area. So the area of the whole semicircle, radius is 6, so the area is pi r squared, right? It's going to be half that since it's a semicircle. So the area of the semicircle, the whole thing, is 4.5 pi. The area of this smaller semicircle, the 4 centimeter and the 2 centimeter ones, add them up, it's 2.5 pi. So the area that we want is going to be subtracting those. 4.5 minus 2.5 pi is 2 pi. So then the area we want is 2 pi, that's the shaded region, divided by the total area, 4.5 pi. Pi's cancel out, luckily. You get 2 divided by 4.5, which is 4 out of 9. What would be the probability that we pick in there? I don't know. We'll figure it out later. Now, theoretical probability is what happens kind of in general. You flip a coin, you got a 50% chance of getting heads, a 50% chance of getting tails. That does not mean you will get heads and tails half the time. If I flip that coin twice, it doesn't mean I'm guaranteed one head and one tail. I could have heads twice, I could have tails twice. I could have heads and tails or tails and heads. There's all different ways this can happen. Rolling dice, who knows? You could roll a 1 3 times in a row. You could never roll a 1. It's just, anybody who's played any kind of board game understands what I'm talking about. So what really happens, this is called experimental probability. You can estimate probability of an event using data or by using an experiment. We'll actually do this in class next week. But for example, if a doctor states that the operation has an 80% probability of success, that means that in the past, 80% of the people that have had that surgery or had that operation had a favorable outcome. It's not based on random chance, it's based on what has happened in the past. Each repetition of an experiment is called a trial, and the sample space of an experiment is the set of all the possible outcomes. So it works kind of the same way as traditional or theoretical probability, but this time it's the number of ways an event actually occurs compared to the number of events or the number of trials. So it's a little bit different. What we get is a frequency. And so let's look at this. This bar graph shows the results of 100 tosses of this oddly shaped die. It's still a 6-sided die, so let's see. Looks like 1 came up 16 times, 2 came up 21, 3 came up 16, 4 only came up 11, 5 came up 22, and looks like 6 came up, looks like maybe 12 or 13 times. So let's figure out, they rolled this dice 100 times, so that's our number of trials. 3 came up 16 out of 100, so 4 out of 25, it's 0.16. Now, if it were completely random, it would be, guess what, 1.666 repeating. So 1 in 6, 4 out of 25, it's pretty close. What would be the probability of rolling a perfect square? Well, which of these numbers is a perfect square? 1 is, and 4 is. So it looks like 1 came up, 17 times. I'm sorry, I thought it was 16. It's definitely 17. And then 4 came up 11. So 17 plus 11, that's a 28 out of 100, or 7 out of 25. 28% of the time. Now, the probability of rolling a 1 or 4 in general, that's 2 outcomes out of 6. 2 divided by 6 is 1/3. So in this case, actually, the actual probability of rolling 1 or 4 was less than the the theoretical probability. Any number other than 5. Looks like 5 happened 22 times. So we're just going to find the complement of that. 1 minus 22 out of 100 is 78 out of 100. That's 39 out of 50, or 0.78. Now, again, 5 out of 6 would be the probability in general of rolling a number other than 5, and that's 83.3 repeating percent, so about 83%. So again, 5 actually happened more frequently than it should have based on theoretical probability. But again, this is what happened in this 100 tosses of the die. It might be different if they toss the die another 100. That's just the difference between experimental and theoretical probability. So let's go back to the note sheet and let's look at this. So here's another example. This is a spinner. You remember the spinner, red, yellow, blue, green, 4 outcomes. They spun it and they got 30 times they spun red, 25 yellow, 12 green, 33 blue. They spun it, add them all up, a total of 100 times. So what would be the probability that we roll red? So the probability of red is 30 out of 100, or 0.3. Probability of yellow would be 25 out of 100. The probability of spinning green or blue, add them up. 12 plus 33 is 45 out of 100. That's about 45%. So let's look at this. Another spinner. This one has numbers instead of colors. Same idea. There's 4 possible choices here. How many spins were there in total? Let's see. Let's add up these spins. Add them up. And what do we get? 15 plus 10 plus 8 plus 22 is 55. So they spun the spinner 55 times. What's the probability of spinning a 3? That would be 8 out of 55, which is about 14.5%. Even numbers, that's 2 or 4. So that would be 10 plus 22 out of 55. So 32 out of 55 would be about 58%. Well, 58.2%. 1 or a 2. That would be 15 plus 10 out of 55. That is 25 out of 55, which is 45.5%. And this is all based on data instead of based on just what do you expect to happen. Really, if you spin these spinners, you expect it, well, in 55 trials, well, you expect a 1 in 4 chance every time. You expect to get 1 1/4 of the time, 2 1/4 of the time, and so on. So like an even number, you would expect to get that half the time. Half of 55 is 27.5. Here, it was, a lot more than that. It was 58% instead of 50%. So that's basically it. So your homework's going to be in the assignment sheet. Click that like button if you learned something today, and I will see you guys in the next one.